Hello, calculus fans. All right, so we're going to work on some optimization problems. So in this problem, what we're going to do is design a cylindrical can. This can is going to be made to hold 2 liters of water. Now the sides are going to be made out of a material that costs 20 cents per square centimeter. Now the top and the bottom of the can need to be made out of a stronger material. That material is going to cost twice as much as the sides per square centimeter. Okay, so we want to find the dimensions, that is, the base radius and the height of the can, that are going to minimize the cost of the metal that is used to manufacture the can. Well, let's take a look at the picture of the can that we're going to make. So this is a rough sketch of the cylindrical can that we want to build. Now it may be of a different dimensions than this. It may be short and squat. It may be something in the middle. Now we have the freedom to choose these things, the values of R and H, as long as in the end we make something that holds 2 liters of water. We may end up building something tall and thin, like a Red Bull can, or we may end up making something flat and wide, like a tuna can, or it could be something more in the middle, like a can of Coke. So let's cut this cylinder open into pieces. We're going to remove the top and the bottom, and then once we remove the top and the bottom, then we essentially have this thing going around the side that we can cut open and lay flat. Now let's see what it looks like when we break it open into pieces. So we remove the top and the bottom, and then after we do that, we cut along this line. So the line that we're thinking about is here along the side of the can. We cut there, we slice it, and then we unfurl it and lay it flat. And then we end up with this rectangular slab here. So the rectangular slab has height h, which is the same height as the cylinder, and then the other dimension is 2 pi r. And that's because if the cylinder has base radius r, then the circumference of the base is 2 pi r, and when we unfurl this thing, then that's what we're going to get for the length of the side of that rectangular piece. Now the area of the top and the bottom of the can are pi r squared. Now that we have the dimensions of the side after it's been unfurled, it's going to be 2 pi rh. Now sometimes you see the area of the side of a cylinder referred to as the lateral surface area. And the word lateral means side. Now let's write down a function for the cost. The cost to manufacture the can. So the cost to manufacture the top and the bottom is 40 cents per square centimeter. Keep in mind that all of our measurements here, the R and the H, are measured in centimeters. So our first term in the cost here is 40 cents times the area of the combined top and the bottom. Now the area of each one is pi r squared, but there's 2 of them, and so that's why we have a 2 in there. For the other piece, we just have 20 cents per square centimeter times 2 pi rh. And so the 2 pi rh is the lateral surface area of the cylinder. Once we clean everything up, then this is the expression that we get for the cost of to manufacture the cylinder. So you give me the R and the H, whatever dimensions that you want, I plug it into this formula that tells me what the cost of manufacturing will be. Okay, so now we're going to eliminate a variable. Now we're given in the original problem that the can is supposed to hold 2 liters of water. Now there's 1,000 cubic centimeters in a liter, so the volume of the can is going to be 2,000 cubic centimeters. And we know that the volume is given by pi r squared h. That's the formula for the volume of a right circular cylinder. So we're going to set the pi r squared h equal to the 2000, and we'll solve for h. So we have pi r squared h is equal to 2000. And then if we solve for h, we're going to get 2000 over pi r squared. Now what we want to do is go back to our cost function and substitute in this value of h. So remember that we previously computed this cost function, 0.8 pi r squared plus 0.4 pi r h. And now we're going to substitute in this value of h in here for h. So we get something that looks like this, and let's try to simplify it. So we end up with a cost function of 0.8 pi r squared plus 800 over r. Let's think about what we've done here. Previously, we had an expression where we could plug in values of r and h to get the cost. Now, since once we know the value of r, we know what h is, then this constrains us. And so just knowing the value of r is enough to be able to compute the cost. And so this expression right here will give us the cost just as a function of r. Now this is the cost, so we're trying to make it as small as possible. So the function that we want the absolute minimum of is this thing. We want the absolute minimum of c of r equals 0.8 pi r squared plus 800 over r. The value of r can be any positive number. Certainly it can't be 0, we're measuring a radius. And it can be as large as we like. If r gets really big, then we have to compensate that for that by making h really small. So if we're trying to find the absolute minimum of this, then let's try to find critical numbers. Now in order to find critical numbers, we need to take a derivative. So the derivative is 1.6 pi r minus 800 r squared. Notice that we can use the power rule to differentiate this. We don't need the quotient rule. Let's try to simplify this algebraically. So we end up with 1.6 pi r cubed minus 800 all over r squared. Now we're going to set this equal to 0 to find a critical number. So if we set this equal to 0, then we're going to end up with r equals the cube root of 500 over pi. Now don't take my word for it. Do the algebra, work it out, take this equation here, and try to solve for r. You should see that that's the only critical number. Now the domain of the function that we're looking at is 0 to infinity, which is not a closed interval, so we can't use the closed interval method. But we can take note of the fact that the derivative is negative when we plug in values that are less than the critical number, and the derivative is positive when we plug in values that are bigger than the critical number. Well, that tells us that the function is decreasing until we hit that critical number, and then it's increasing. And so that tells us that this critical number has to represent an absolute minimum. If we work out that number, that's about 5.4 centimeters. That has to give us the absolute minimum. We're talking about the absolute minimum cost here. Now we can also go back and figure out the height. We had calculated earlier that the height is 2,000 over pi r squared. So if we plug in this value of r and work out this number, we get a height of about 21.7 centimeters. So that's it. The conclusion is that we should make a cylinder with radius about 5.4 centimeters and height about 21.7 centimeters. Those dimensions will minimize the cost of manufacturing our can. Okay, that's all for now.